In this class, we will discuss about the boundary conditions that are applied in solving torsion problems and also the behavior of a circular cross section subjected to torsion. So here, to understand the boundary conditions, I will consider an arbitrary area of the shaft like this. It is subjected to a torque T like this. So due to that torque, some point on the boundary P is shifted to P dash. And let me take the dimensions of this PP dash as ds and this as the dx and this as dy. So from this elementary figure, so if you draw a normal, n is a normal which is drawn to this boundary PP dash. And if this angle you have, if it is taken as theta, then you can see, observe from this diagram, cos theta is minus dx by ds. This is minus because this point P shifted towards left. So left is towards left, therefore it is taken as negative. Whereas this dy is taken as positive because P has shifted upwards, therefore it is positive. So cos theta is minus dx by ds and sin theta is dy by ds. And from another definition of direction cosines which we have learned already, so this cos of the angle between the normal and the x-axis, that is denoted by L, that is direction cosine, and cos of the angle between this normal L and y-axis, that is taken as M. So the boundary condition for this torsion problem, you have to remember this. You can derive this, but now I am not doing that. So just remember this equation, because all the other stress components are zeros in torsion problems, that is sigma x, sigma y, sigma z and tau xy. All the four stress components are zero, only these two exist. Tau xz and tau yz exist, and if you apply the general boundary condition to that particular torsion problem, then you are going to get the boundary condition in this form: tau xz into L plus tau yz into M is equal to 0. Now this is nothing but L is nothing but cos of the angle between normal and x-axis, that is minus dx by ds, dy by ds. So this becomes L, and because when you take like this, so if you draw the x and y axis here, this becomes theta. So therefore L becomes dy by ds and M becomes minus dx by ds. Now if you substitute those things here, so you are going to get tau xz into dy by ds minus tau yz into dx by ds is equal to 0. Now if you once again substitute for tau xz and tau yz in terms of warping function, psi is a warping function. So this I have explained in the last video, you can just go through that. So tau xz is nothing but dou psi by dou x minus y. So into dy by ds, and tau yz is nothing but dou psi by dou y plus x into dx by dx is equal to 0. So this is called as the general boundary condition for solving any torsion problem. So here psi is called as the warping function, which is a function of x and y. X and y. So because warping takes place in general in non-circular sections, whereas in the case of circular sections, this warping effect is not there. But anyway, we are deriving the condition for general sections, that is both circular and non-circular sections. And another equation in terms of psi, that is warping function that should be satisfied, is the Laplace equation, which is dou square psi by dou x plus and dou square psi by dou y square is equal to 0. This also I had explained in the earlier video. You can just go through that. That means in order to this psi to be a warping function, these two conditions should be satisfied. Laplace condition should be satisfied as well as this boundary condition should be satisfied. So this is the general boundary condition we have to remember. Now we can get an expression for the torque applied by knowing the shear stress values. You can obtain the torque applied by using this equation. So torque applied in general for any type of cross section, T is equal to integral over A means area here, whatever area you are covering, cross section area you are covering, tau yz into x into dA minus tau xz into y into d. So how to get this is, so here we know that tau yz is stress. Stress multiplied by this area gives the force. Force into x is the distance. So force into distance is the torque. So here tau yz, so you can see here tau yz will be acting like this. I have written here, tau yz will be acting like this, and that should be multiplied by the distance x. Please note that. So tau yz will be multiplied by x distance, and tau xz will be multiplied by y distance. Okay, this is the distance. Y distance you have to multiply. So you can find one another thing is, one is giving tau yz, suppose if it is giving anti-clockwise, tau xz will be giving clockwise. So that means they are of opposite nature. The torque developed by tau yz and tau xz, they are of opposite nature. That's why I have taken minus sign here. Now here, what happens? We have to substitute for now this tau yz in terms of phi. So we have defined in the last lecture. I have given an expression for tau yz as minus dou phi by dou x, and the tau xz as dou phi by dou y. So these I have explained in the last video. You can just go through that. When phi is called as the stress function, Prandtl stress function. So psi is working function and phi is Prandtl stress function. So using both phi and psi, you can express this shear stresses. So this is the relation between the shear stress and the Prandtl stress function. Now if you substitute that, for tau yz you can substitute minus dou phi by dou x, and for tau xz you can substitute dou phi by dou y here. And this dA can be taken separately, so that dA can be written as dx into dy, because elemental area means I am considering a rectangular area, so dx into dy becomes the value of dA now. Now here minus you can take outside, so it becomes dou phi by dou x into dx plus dou phi by dou y into dx dy. Now this can be integrated by separating the variables. So this is the separating the variables, or integration by parts, you can say. So if you do that, so what happens here? There are two terms here. So these two terms can be separated here. So what we have done here is this minus is there into this integral dy I have taken separately, x into dou phi by dou x into dx separately, plus next integral dx is taken separately into integral y into dou phi by dou y into dy is taken separately. This is nothing but integration by parts. So you should remember that integration part by parts. Let us not go in detail about that. It's a mathematical part, calculus part. So integrate by parts and putting phi is equal to 0. So here we can always prove that this Prandtl stress function phi is 0 at the boundary. So I am skipping that derivation, but you can just remember that at the boundary means S is the boundary here. So S is the boundary. So this is the boundary. Along the boundary, the Prandtl stress function is 0. Phi is 0. So if you put all those things here and integrate by parts, you are going to get finally T is equal to 2 times double integral of phi into dx dy. So this is the expression for the torque, applied torque. So applied torque we can find out by knowing the Prandtl's stress function. If you know phi, you can calculate T. So for any type of cross section, this formula is valid. Next, let us check for the case of a circular cross section. When a circular cross section is subjected to torsion like this, so R is the radius of that circular cross section. So when it is subject to torque like this, what are the stresses that are going to develop, and how we can get the torsion equation from that? So this, of course, one approach you have done using strength of materials. You got the torsion equation. Here also you get the torsion equation. T by J equal to tau by R equal to G theta. So same equation you are going to get, but this is elasticity approach. Now in this approach, what we do is we are going to assume a warping function. So since in circular cross section, so there will not be any warping, let us assume some constant. So it is some constant. Warping function I am going to assume a constant here. Now let us apply the boundary condition for the warping function. The boundary condition is this: dou psi by dou x minus y into dou y by dy by ds minus dou psi by dou y plus x into dx by ds is equal to 0. So let us apply that equation here. So since psi is constant here, dou psi by dou x is 0, dou psi by dou y is also 0. So both of them are 0 because it's a constant. So therefore it becomes 0 minus y into dy by ds minus 0 plus x into dx by ds is equal to 0. Or we can write this as y into dy by ds plus x into dx by ds is equal to 0 by removing that minus sign. So if you integrate this, you are going to get d by ds. Of course, I have separated it. So d by ds So that if you integrate, you are going to get this as d by ds of x square plus y square by 2 is equal to 0. So or x square plus y square is equal to a constant. So it is equal to a constant. So we can remember that this is the equation of a circle. So this is the boundary of a circle. X square plus y square is equal to r square is the equation of a circle with center origin that we have studied. So the constant becomes r square here. That means if you assume psi is equal to a constant, warping function is a constant, you are going to get the cross section as a circular cross section. So this is the reverse way. Now let us take the warping function. Warping function I will take it as psi. We know that earlier we have taken the W is displacement in the third direction, So we have the W is related to warping function like this. W is equal to theta, which is the angle of twist per unit length, into psi of x comma y. So here psi of x comma y we have taken it as constant. So therefore theta into c we are going to get. Now let us find out the polar moment of inertia. According to the definition of polar moment of inertia, it is double integral x square plus y square dx dy. Okay, or it can be in mechanics you might have studied it as ixx plus iyy. So that is your polar moment of inertia. So but we know from the basics of SOM, d by j is equal to g into theta. We know this. So the theta is the angle of twist per unit length of the shaft. From this, therefore, theta will be equal to t divided by g into j. So g is the rigidity modulus or modulus of rigidity or shear modulus. J is the polar moment of inertia. T is the torque. So this is the relation between angle of twist, torque, rigidity modulus, and polar moment of inertia. So if you substitute this theta here, so W is equal to this theta will be T by Gj into C. That here it is once again this is a constant because T, G, J they are all constants and C is also constant. Therefore W becomes a constant. So that means it's not a function of x and y. Thus the cross section does not warp. So there is no warping in the case of circular cross section. It is independent of x and y. Now from this we can always calculate the shear stresses that are induced in a circular section. So tau xz according to the definition in terms of this angle of twist. In the last video I have explained about this. Tau xz is d theta into dou psi by dou x minus phi. So here since psi is constant here, so this derivative becomes 0. So therefore this becomes minus d theta y, or for theta if you substitute t by gj, so this becomes minus t by j into y. So that is the expression for tau xz. Similarly, tau yz is d theta into dou psi by dou y plus x. Once again here dou psi by dou y is 0 because psi is constant and this becomes d theta x. Once again if you substitute for theta as t by gj, so this becomes t into t by gj into x, that is t by j into x. So these are the two values of shear stresses, tau xz and tau yz. From that you can calculate the resultant shear stress tau. Resultant shear stress tau is nothing but square root of tau square yz plus tau square xz. If you substitute these things there and simplify, you are going to get t by j to root of x square plus y square, and then root of x square plus y square is nothing but r, because r square is x square root x square plus y square. So t by j into r. That means finally you are getting tau is equal to t by j into r, or you can write all these three together. So t by j is equal to g theta, and that is equal to tau by r. So t by j is equal to tau by r is equal to g theta. This is your pure torsion equation which we can derive in strength of materials also. But anyway, this I have applied for circular section by taking the warping function as constant. That's what I have done here. By assuming suitable warping function, you can always arrive at the torsion equation. Now here another thing is what is the angle alpha made by this resultant shear stress tau with the horizontal or with the plane of tau xz. So that is given by tan alpha is equal to tau yz divided by tau xz. If you substitute, so then the t by j will get cancelled. So it will be left with minus x by y. So that is the value of tan alpha. So this is how we can explain the concept of torsion subjected to applied to circular cross section. So assuming a suitable warping function, you can show that suitable warping function is function is constant here, warp size equal to 0. So you can always prove that this boundary of the cross section is a circle. So that means psi is equal to c, or a constant, represents the warping function for a circular section subjected to torsion. So and then afterwards, by using the concept of polar momentum, inertia and all, so we can always, and angle of twist, so we can always find the resultant shear stress acting on the section, and finally we can get the torsion equation. So please note that in the case of any problem on torsion, so here you can observe that 4 stress components will be 0. Sigma x 0, sigma y 0, sigma z 0, tau x y 0. Only tau x z and tau y z they exist. Similarly, 4 strain components will be 0. Epsilon x 0, epsilon y 0, epsilon z 0, gamma x y 0. Only gamma x z and gamma y z they exist. So this is about the boundary condition that is used in solving torsion problems, and also how the torsion of circular cross section can be analyzed. In the next class, I am going to take about the elliptical section and also thin walled sections.